want to make sure that we finish in good time. So that is why we are going to start. And if there's anyone who is joining us, they're going to join us later on. But we're going to start. Right. So like I said the other time, we're going to start talking about Mécanique du point matériel. So there are a few interesting topics that we have to first of all talk about. And maybe let me just find out from Natasha. Natasha, are you able to get me? Because you didn't. Yes, Natasha.
Sorry, yes, I can get you.
Right. So that is good information. So we want to talk about Mécanique du point matériel, and then in the first session we want to talk about cinématique du point matériel, and then right. So in the first session we want to talk about cinématique du point matériel. But before we talk about cinématique du point matériel, I want us to look at a few mathematical operations, like taking the dot product, taking the vector product, and of course some interesting mathematical calculations that we're going to perform as we are talking about cinématique du point matériel, and then the mouvement relatif, changement de repère, and then finally dynamique du point matériel. So we first of all have to make sure that we are comfortable with the different mathematical concepts that we're going to employ later on to avoid confusion. And of course, I sent a document in the group. It contains two exercises on what we're going to be talking about today. So it contains two exercises. And of course, I'm trying to record this session as I'm teaching so that I can make it available for you later on. And of course, if it fails, I'll still try to, over the weekend, make videos that I'll send to you so that you can, make reference to and all that good stuff. Right, so let's look at a few mathematical operations that are going to be very important as we are discussing whatever we're going to discuss in this session, which is cinématique du point matériel. So what is a vector? Now, the first thing that we want to define is the idea of vectors. So a vector is going to be a quantity that is going to have. Now, of course, I've moved to the board. If the screen disappears and if you are unable to get me, please give me a signal, because I don't know what is happening in the meeting because I've moved to the board. Right. So let's first of all define what a vector is. So a vector is going to be a quantity. So a vector is going to be a quantity that is going to satisfy that is going to have three main characteristics, right? So let's say we have a vector v. We're going to say that v is going to be a vector. So v is going to be a vector if it satisfies the following, the following properties. Now, the first property is that it has to have what is known as direction, right? So we must have direction. So I'm just following the notes that you sent me, the polycopy, and of course other documents that I found online to sort of like supplement whatever we have. So a vector is going to have direction. Now, of course, let me make sure that I write that properly. So a vector is going to have direction. So apart from this important aspect, it is going to have what is known as a sense. And then number three, a vector is going to have what is known as a magnitude, or what we're going to call, a norm, right? So a norm. So a norm is going to be basically the magnitude of the vector v. So these three things are what are known as, the characteristics. This is what makes up a vector. So this is what a vector is going to have. A vector is going to have a direction, is going to have a sense. It's also going to have what is known as a norm, or a magnitude. And then generally, what we have is we use, lines like this with an arrowhead. So let's say this is a point A, and then this is going to be the point B. And we want to draw the vector that is, from A to B, we're going to use a line segment. And then we're going to, add this, arrowhead to show the direction of the vector. So this is, can be written as, A, B. So I'm sure you're familiar with these concepts. So let's now talk about. Now I'll be moving quickly on. I'll be moving quickly on things that I feel, we are already familiar with. of things that I feel we already know, and then I'll slow down on things that are going to maybe be a little bit new for everyone, right? So we have this, and let's talk about collinear vectors. So we're going to say that two vectors are going to be collinear. Now I'm just going to allow myself to write everything on this page like so. We're going to say that two vectors are going to be collinear. So let's say the vectors u and v are going to be collinear. So they're going to have this property, meaning they're going to be collinear if the vector u is going to be equal to some scalar alpha multiplied by the vector v, right? So the only difference between these vectors is probably the length. So we can sort of like, try our best to, let me just get rid of this point A here and this point B here, and of course this AB like so. So let me also use a different color and draw another vector, in the same, right, like so. So this is going to be, the vector in red can be our vector u like so. And then when we scale this vector u by some quantity alpha, we're going to get the vector v. And of course, let me just use the same color so that we, let me just use the same color here for the vector v like so. So if I have the vector u and I scale this vector u by some quantity alpha, I'm going to get if I get the vector v, well, this is what it means for these two vectors to be collinear. So they are basically, they're pointing in the same direction. Meaning they have the same sons in the same direction, and then the only difference is the length or the magnitude. So we're basically scaling either u or v by some quantity alpha. So this is what it means for two vectors to be collinear, right? And we'll see how this is going to help us later on. Another important, concept to know is the idea of unit vectors. We'll be talking about points. Cinématique du point matériel. We'll be talking about what is known as a repère or a référentiel. We'll talk about the difference between these two terms, a repère and a référentiel, but that is what we'll be talking about. And of course, we're going to position ourselves in some 3D space, and then we're going to use either the Cartesian coordinates, the cylindrical coordinates, and of course the spherical coordinates. And then when we are in 2 dimensions, we can think about the polar coordinates or the Cartesian coordinate system, right? So we'll be talking about those things. And of course, we'll say that the unit direction of vector for the x-axis or along the x-axis is going to be the vector I, and then the unit direction of vector along the y-axis is going to be the vector j, and then for the z-axis we're going to have the vector k. So those vectors I, j, and k are unit vectors, meaning their magnitude is going to be 1. So a vector with magnitude 1 is going to be known as a unit vector. So along the x-axis we have a unit vector, and of course these are going to be used to sort of like give us the direction of the vector, or the direction of the vector. We're going to use those unit vectors. And then in general, if you have a vector v in general, right? So this is going to be in general. In general, if you have a vector v, say we have a vector w like so. If I want to normalizing means I want to divide a vector by its magnitude. If I want to normalize this vector w, all I have to do is divide this vector w by what? By its magnitude, and then I'm going to get a unit vector. If I normalize this vector, I'm going to get a vector of unit length, right? So that is the idea. So a vector of unit length is going to be, if I say I'm going to have a vector u like so. If I divide this vector w by its magnitude, so its magnitude is going to be, the magnitude of a vector v is going to be, so I'm going to use these 2 lines, and then I'll tell you what these 2 lines mean. So this is norm, right? Norm is different from the absolute value, right? Norm and the absolute value are different, right? So the norm, I'm talking about the norm of the vector, just like I've written here. So we divide a vector by its norm. What we're going to get is going to be a vector of unit length. So this is going to give us a vector of unit length. So vector of unit length. Now I'm sure that most of you are familiar with this, so I'm just going to sort of like cruise here. So a vector of unit length, vector of unit length, like so. Right, now let's look at the operations we can perform on vectors. What operations can we perform on vectors? Now let me just allow myself to create a new page, like so. So what operations can we perform on vectors? Now the first operation is what you guys have already predicted. So let's say we have two vectors. So let's look at operations we can perform on vectors. Now operations we can perform on vectors. So let's say we have a vector A and we have a vector B, like so. Now the first operation we can perform on these two vectors is the addition operation. Now addition, so here we have A plus B is going to be the sum of these two vectors. Now in Mécanique du point matériel, we'll be talking about 3D spaces, or we'll put ourselves in a 3D space. So meaning every vector is going to have 3 components. So if you want to perform the sum between the two vectors, you have to add the corresponding components. So the x component of A and the x component plus the x component of B, that gives you the x component of the sum of the two vectors, that is A plus B. And then the same thing, the y component plus the y component, the z component plus the z component. So what we are saying here is, in Mécanique du point matériel, we'll be putting ourselves in a 3D space, such that every vector is going to have 3 components. So let's say the vector A in this case is going to have, what are the components of the vector A? Well, simple mal, you can choose whatever you want here. So I'm just going to say, here we're going to have some x, and then some y, and then some z. So meaning the x represents the component along the x-axis, the y represents the component along the y-axis, then the z represents the component along the z-axis. So if I do the same thing for B, but of course A and B don't necessarily have to be the same vector, they can be different vectors. So what I'm going to do is that here I'm going to say x prime, and then y prime, and then z prime. Now the sum A plus B, now let me just descend a little bit here. So the sum A plus B is going to be, so A plus B is basically going to be, so we'll add the corresponding components. So we're going to have x plus x prime, and then y plus y prime, and then finally z plus z prime. Now of course A minus B is the same thing. We basically subtract the corresponding components. So we have x minus x prime, and then y minus y prime, and then z minus z prime, like so. So this is what we have. So this is addition, and then this is subtraction. Remember, we can also scale a vector, that is increase its length or decrease its length. If I multiply a vector by a quantity 2, by a scalar quantity 2, then its length is going to increase by 2, because in every aspect. So along the x the axis, the y axis, and the z axis, so we increase its length. But if I multiply it by something like 1/2, I'm going to sort of like reduce the length of the vector in every aspect. So the x axis, the y axis, and the z axis. So we also have scalar multiplication. So we'll talk about, we also have scalar multiplication. So what is scalar multiplication? Now another way of writing A is, instead of writing it in column form, instead of writing A in column form, or instead of writing B in column form, when we are in the, we'll talk more about this when we sort of like get to the Cartesian coordinate system. But of course we can sort of like write it in one line, where we multiply x and the unit directional vector along the x-axis, and then y and the unit directional vector along the y-axis, and then z with the unit directional vector along the z-axis. So we'll get to that when we sort of like get to the part where we're talking about the Cartesian coordinate system and the other coordinate systems that we're going to talk about. So that is the sum, right? And I'm sure you are also familiar with most of these concepts. You're familiar with most of these concepts. So that is how you add the two vectors. Now we can also have addition and subtraction. So let me just say addition and subtraction, like so. Now the second operation is what is known as scalar multiplication, or we're going to say multiplication par un scalaire. Multiplication par un scalaire. Multiplication par un scalaire, like so. So if we have a vector v, remember, we'll be positioning ourselves in a 3D space. So we're putting ourselves in the 3D space. So the vector v here is going to have three components, x, y, and z, like so. Multiplication par un scalaire, and then let's get some alpha that is going to be a real number, like so. Multiplication par un scalaire simply says, alpha multiplied by v is basically going to be alpha, and then here we're going to have x, y, z, like so. Then this is going to be equal to alpha x, alpha y, and then of course alpha z. So this is multiplication par un scalaire. So we are scaling the vector. Scaling, multiplication par un scalaire. There's another product that we'll talk about, which is multiplication vectorielle, or when we'll be multiplying vectors. We'll talk about the dot product, we'll talk about the vector product and all that good stuff a little later. Right? So that is multiplication par un scalaire. So let's talk about now the dot product. Now, is everything all right? Are we able to follow, or have we gotten disconnected? Is everything okay? Bien. Right. Bien. So let me just go back to the board, like so. So multiplication par un scalaire, we'll now move to the dot product. Well, the dot product is basically going to be, so if you have a vector, and then you want to take the dot product between two vectors, the result of us taking the dot product is going to be a scalar. It's going to be a scalar. There's another multiplication for vectors which is known as produit vectoriel, that is going to give us a vector. That is going to give us what? That is going to give us a vector. There's another which is produit vectoriel, but then produit scalaire is going to give us a scalar. So produit scalaire. So let's say we have two vectors. Now let me just allow myself to again use once more v and maybe w this time. So let's say we have x, y, and z, like so, and then w, like so. And of course here we're going to have, maybe let's say here we have x prime, y prime, z prime, c'est pas mal. So you can choose whatever you want, but in general these are not going to be equal, right? So that's why I'm saying x prime, y prime, to sort of like place a distinction between the components of these two vectors. Well, what the dot product is going to do, so let me just say v dot w, like so. What the dot product is going to do is that we're going to multiply. So it is x, and then we take the sum. So x, then we take the sum. So we're going to say x prime plus y prime plus z prime. So this is a scalar product. So this result here is going to be a scalar. That is why it is known as produit scalaire. So it is going to be, the result is going to be a scalar. So the scalar product is going to be commutative. So this is, if I say w dot v, well, I'm going to get the same thing, because I can sort of like change the positions of these two vectors, and I'll get x prime x plus y prime y plus z prime z. Or we know that multiplication is going to be multiplication as an operation is commutative, so meaning I can sort of like get back to x prime and then plus y prime plus z prime. So we see that this dot product is going to be commutative, like so. Très important. And then of course we also have another formula for the dot product, and I'm sure this is a formula that most of us know. So let's say we have two vectors. We have the vector v, and then let's say we also have the vector w, like so. And then there's an angle of there's an angle theta degrees between these two vectors, that is v and w. So if I want to allow myself to calculate the dot product, so the dot product in this case, v dot w is basically going to be equal to the magnitude of the vector v, right? La norme de v, so multiplied by norme de w, which is the norm or the norm or the magnitude of the vector w, like so. And then I take cosine. Now let me just allow myself to sort of like write on a bigger space. So V dot W is going to be equal to la norme de V, and then multiplied by la norme de W. And then if I take cosine of, whatever is in between, of whatever angle is in between here, I would have calculated the dot product, right? And then one important property is that if the two vectors are perpendicular, then the dot product is going to be equal to 0. So see, if we have that V is perpendicular to W, if V is perpendicular to W, then the dot product V dot W is going to be equal to 0. So the dot product is going to be 0 if the two vectors are perpendicular. And then of course more about dot products when we get to the coordinate systems, that is the Cartesian coordinate system and their respective unit directional vectors. We're going to sort of like talk more about this dot product and what it is going to help us do later on, right? So let's now look at produit vectoriel. Produit vectoriel, unlike the, yes, is that a question or?
No, I just wanted to repeat on the one. You said that it's a particular then.
Yeah, okay. Okay, this is one consequence of the scalar product. If the angle between the two vectors 90, so let me just maybe say, if the angle between V and W is equal to 90 degrees, if the angle between the two vectors is 90 degrees, alors the dot product is going to be what? The dot product is going to be 0. That is what we are saying here. So this is a consequence. So we can say consequence of the dot product. So the consequence is that if the two vectors V and W are perpendicular, then the dot product is going to be equal to the most awesome 0, right? So let's now look at, is that okay?
Yes.
Right. So let me just move to produit vectoriel. Now let me just quickly move to a produit vectoriel. Unlike the scalar product, the result of a produit vectoriel is going to be, of us taking a produit vectoriel, is going to be a vector, right? It is going to be a vector. So let's say this time I'm going to allow myself to, now of course this is 3, and then this is going to be point number 4, or property or operation number 4. Now let's allow ourselves to sort of like choose, maybe let's say, what vector can we choose? Simple mal, you can choose whatever you want. So U, and then you have X, Y, and Z, like so. And then let's say we give ourselves the vector V, like so, with components X prime, Y prime, and Z prime. So how do you take the vector product? So the way we'll be doing it is, we'll say U vectoriel, so we'll say U vectoriel V is going to be equal to what? So I'm just going to draw a horizontal line here, a vertical line. So this is what you would want to do. One horizontal vertical line there, and one vertical line there. And then I'm going to sort of like put the symbol here to show what operation I'm taking. So it's a produit vectoriel. And then I'll write the components of the first vector down, so like so, X, Y, Z, and then the components of the other vector, that is X prime, Y prime, and of course Z prime, like so. So le produit vectoriel, how do I compute le produit vectoriel? Well, the result here is going to be, so the result is a column vector. It's a vector that is going to have this, the same number of components as the two vectors. So if you want to calculate the X component of a produit vectoriel, if you want to calculate the X component, all you have to do is you have to, sort of like get rid of the first line. So I'm just going to cross this first line here. And by crossing this first line here, I'm now going to sort of like cross multiply the other two components. So I'm going to say Y multiplied by Z prime minus Z multiplied by Y prime. So that is what I'm going to do. Let me just get back to this original color. So we'll have Y multiplied by Z prime minus Y multiplied by Z prime minus Z multiplied by Y prime. So this is the X component. To find the Y component, I'm basically going to get rid of this second line, like so. And then I'm going to cross multiply the first and last line. So I'm going to have, then here, this is where you have to pay, this is where you have to be very careful here. Before writing anything along the y component, you're going to put a minus, you're going to put a negative, and then write, and then you can write whatever you want, whatever is supposed to be written here, the result of the cross multiplication. You put a minus. This is only for the y component, only for the y component. So we're going to say x multiplied by z. So it is x multiplied by z prime, and then minus x multiplied by z prime, and then finally z multiplied by x prime, right? Z multiplied by x prime, only for the y, only for the y. And then for the z component, now we basically do the same thing, but this time we're going to sort of like get rid of the last line, and then we sort of like cross multiply the two lines that are on top. So here we have x multiplied by y prime, so x multiplied by y prime minus x multiplied by y prime, minus, and then x prime multiplied by what? Multiplied by y. So this is going to be our produit vectoriel. Now this is going to be composant 1. This is going to be composant 2. This is going to be our composant 3. Is everything okay? This is how we do our produit vectoriel. C'est bon? Right. So, right. Now let's talk about it. Let's talk a little bit more about this vector product. So unlike the scalar product that is commutative, the vector product is anti-commutative. So in general, u vectoriel v is not equal to v vectoriel u. I cannot swap the positions. So it is going to be anti-commutative. The vector product is anti-commutative. Commutative, like so. Then it's anti-commutative. So if I want to have equality here, what I have to do is when I change the positions, I have to put a minus in front. So this is going to, if I say u vectoriel v, if I want to sort of like change the positions, all I have to do is say v, but then I'll put a minus in front and then say vectoriel u, like so. If I want to change the positions, this is what I'm going to do. So the vector product is anti-commutative. So what happens when two vectors are parallel? Donc si two vectors, that is u, if two vectors if u is parallel to the vector v, alors le produit vectoriel is going to be nul. It's going to be 0. If the vectors are parallel, if I take the vector product, the result is going to be 0. Okay? If I take the vector product of two vectors that are parallel to each other, alors the result of the vector product is going to be 0. Another important detail that is worth mentioning is the fact that if the vectors, yes, is that a question?
Yes, it's a question. I want to ask, here you want to put the negative, when you said you want to change, if you want to change the position
Yeah.
of the vector
Yeah.
and the commutative,
Yeah.
you only put the negative on the v, vector v.
Yes. However, if you have me putting a -1 there is sort of like multiplying by this -1. So I can say this is equal to alpha. This is equal to alpha. So in general, this alpha can be anywhere. You can put it in front of v, the alpha. If you have a scalar, you can put it here or you can put it here. Okay? But then this minus is sort of like attached to this v here. I'm putting it on the v side here. But in general, what is happening here is I have a scalar -1 that I'm multiplying by the vector v. And then the scalar can either be at here or here. So we'll look at these things a little bit later when you sort of like start talking about questions, and when we start answering questions and all that good stuff. And yeah, so this minus is attached to this v, just like to be more precise, it's just like the scalar -1. Okay, so it's sort of like I'm multiplying it only with this v that I have here. Right.
So does it mean that V is the one that's going to change the position, or also the vector U is going to change the position?
I didn't get your question. Come again.
I'm saying since
Mm-hmm.
this is used when you want to change the position, since these two are anti-commutative.
Yes.
So if we put this minus attached to the vector V, then also the vector U will change its position, or only vector V will change.
Well, it's only vector v that will change. We'll multiply -1 by every component of the vector v. So if v has components x, y, and z, what we're going to do is, before taking the vector product, we take negative of every component. Okay, so if we have x, y, and z, we'll have -x, -y, and -z, and then that is going to give us the same result. So let's look at an example maybe. Let's look at an example to sort of like understand what is happening here. Let's look at an example. Let's look at an example here. Let's say we have two vectors. I'm going to take very simple vectors. I'm going to take very simple vectors so that we sort of like don't waste a lot of time trying to sort of like see. So let's say u is the vector. Let's say 1, 1, 1, like so. Simple mal. You can choose whatever you want. So let's say we have the vector v is 2, 0, 0, like so. Now let's say, what is u vectoriel v? What is u vectoriel v? C'est simple. What you have to do is, just like I did, you draw two vertical lines, like so, one here, and then you position one here, and then the operation we are taking here is le produit vectoriel. So what are the components of u? We have 1, 1, 1, and then what are the components of v? We have 2, 0, 0, like so. Oh, we're taking the vector product, so this is going to be equal to, remember, that to find the x components, we get rid of the first line here. So we'll have 1 multiplied by 0 is 0, minus 1 multiplied by 0 is going to be 0. So that is the x component. For the y component, we put a minus here, and then we get rid of the second line, and then 1 multiplied by 0 is 0, and then minus 1 multiplied by 2 is 2, like so. C'est bon? And then for the third component, we get rid of the last line, and then 1 multiplied by 0 is 0, and then minus 2, like so. And finally, the result is going to be 0. And then 0 minus 2, it is minus 2. Multiplied by the negative, we have 2, like so. And then we have minus 2. Now, let's change the positions. Let's change the positions of v and u. So if I say v vectoriel u, is it going to give me the same result? Normalement, no. It is not going to give me the same result because the vector product is anti-commutative en général, hein? En général. So we'll put a vertical line here, and then we put a vertical line here, and then what operation are we performing here? It is the vector product, right? Then the components of v, we have 2, 0, and 0. The components of u, what are the components of u? We have 1, 1, and 1. I'll do it on the same line. So I'll get rid of the first line, and then I'm going to have 0 multiplied by 1 is 0. 0 multiplied by 1 is going to be 0, like so. And then here I'm going to put a minus. I'm going to put a minus, and then I'll get rid of the second line, like so. And then here we're going to have, I'll get rid of the second line, like so. And then I'm going to have 2 multiplied by 1, which is going to be 2, minus 0 multiplied by 1 is going to be 0. Right? And then I'll get rid of the last line, and then I'll say 2 multiplied by 1 is 2 minus 0. Now, this is going to give me, this is going to be 0, and then minus 2 and 2, like so. You can see that this is not the same. This is not the same result. So this and this are not the same. So these are not the same. They are different. Okay. Now let's calculate minus v vectoriel u. So what is minus v? Minus v is, I'm going to multiply negative by every component of, I'm going to multiply negative 1 with every component of every component. I'm going to distribute minus 1. Okay. So what is minus v vectoriel u? You see that it is going to, normalement it's supposed to give me the same thing. It's supposed to give me the same thing. What are the components of v? The components of v, so I'm going to put minus 2 normalement, and then 0 and 0, because minus 0 and 0 are the same thing in this case. So vectoriel, and then what are the components of u? We have 1, 1, 1, like so. Well, this is going to be equal to, just give me 1 second. Right, so let's now do the vector multiplication here, the vector multiplication. So we'll get rid of the first line. So we'll have 0, right? Because the 0 multiplied by 1 minus 0 again. So for the second one, we'll put a minus in front. We'll put a minus in front, and then we get rid of the second line, and then we're going to have minus 2. Minus 2 multiplied by 1, and then minus 0 if you do the other product. Okay, the other diagonal product. Now for the last component, we get rid of the last line, and then we will have minus 2. Okay, we have minus 2 minus 0. Okay, minus 2 minus 0. We can see that this is going to give us 0, 2, and minus 2, which is the same result as u vectoriel v. So if you want to change the positions, if you have u vectoriel v and you want to change the positions, or you want to say v vectoriel u, you have to put a minus in front of v. Is it now clear now that we've taken an example? Ça va?
Oui, ça va, monsieur.
Ok. Donc je passe. Bien. Let's look at other interesting properties of the vector product. The other interesting properties of the vector product, one of them we've talked about. We've talked about two properties, but then just in case someone missed those properties, we said u vectoriel v en general is going to be anti-commutative. So it's not equal to v vectoriel u en general. And then the second component here is, the second property is that if two vectors are parallel, then the dot product is going to be equal to 0. The vector product, sorry, not the dot product, but the vector product. So the vector product here is going to be, so u vectoriel. Now, of course, this looks like a v, but in this case, u vectoriel v is going to be equal to 0. Like so. Bien. Now the third property is what is known as distributivity. Distributivity with respect to l'opération d'addition. So distributivity. So what this property entails is that u vectoriel, u plus v like so, c'est pas mal. So v like so. So let me just get rid of this. U vectoriel v plus w like so. Well, we can distribute the vector product. So this is what this property is about. So we can say it is going to be u vectoriel v plus. So we'll use this property later on to show, or to sort of like find the expression for what is known as l'accélération d'entraînement and vitesse d'entraînement. We will use this property here to sort of like regroup the terms when we have the sum, and the dot product when we want to regroup the terms and come up with one coherent formula for the vitesse d'entraînement and l'accélération d'entraînement. We'll look at these things a little bit later, right? And then so here we're going to have u vectoriel v, so you can distribute the vector product if you have a sum. Same for a minus here. It's going to work for a minus. Bien. Now, the fourth property is what is known as double produit vectoriel. Double produit vectoriel. So you have u vectoriel, and then inside here we have another vector product, maybe between v and w, like so. Well, this is going to be equal to. Now you have to look for a way to sort of like memorize this formula. So how I remember this formula is, if I have a double produit vectoriel like this one here, if I have a double produit vectoriel like what I have here, how I remember this is I'll take the dot product between this vector that I have here and the second vector. So this is going to be u dot w, like so. And then I'll take the first vector outside here, v, like so. C'est bon? And then I'll put a minus. This is how I remember the formula. I'll put a minus here. It's now u and the first vector because I've already taken the dot product of u and the second vector. So u and the first vector is u and the first vector, which is u dot v, and then the other vector w goes outside. So what is this? This is a scalar, right? So this is some scalar alpha. This is some scalar beta. So this result here is going to give me alpha, and then I'm going to perform un produit. I'm going to sort of like perform what is known as a multiplication par un scalaire before I evaluate this difference. So here u dot w is the dot product, and it gives us a scalar, and then a scalar multiplied by a vector, meaning I'm going to scale this vector. It is multiplication par un scalaire, meaning I have to multiply alpha by each and every component of v. And then same here, u dot v is going to give me some scalar that I'm calling beta here. So u dot v here is going to be some scalar that I'm calling beta, and then I'm going to multiply that scalar beta by w, right? So I'm scaling the vector. I'm performing what is known as multiplication par un scalaire. So again, one more time, how I remember this formula, it is when I have a double produit vectoriel, the first part here, I'm going to say the vector u and the second vector here, in brackets, the second vector, right? U and the second vector, I take the dot product, and then I take the other vector outside, and then now minus, and then u and the first vector, and then I multiply. I take the other vector or multiply, yeah, because we'll perform multiplication par un scalaire later on. That, and then the other vector comes out. Okay, is that a question or what is happening? Let me just allow myself to shift and go back here. Oh, it's about the time. So under 15 minutes. Under 15 minutes. So that is un double produit vectoriel. Double produit vectoriel. C'est bon? Je passe?
Okay.
On the double produit vectoriel?
Yes.
Okay. So on the double produit vectoriel, what do we have on the double produit vectoriel? C'est simple. So, okay, let me just close this. Right. So, double produit vectoriel. So, for a double produit vectoriel, meaning we have the dot product, we have the vector product 2 times here and here, right? Normally, if you sort of like go back to analysis or algebra or anything, it is, when we are performing an operation on 3 items, let's say you want to, you are saying 2 plus 3 plus 4. We first of all start by adding any 2 items, right? If in the case of the, in the case of summation, we first add any 2 items and then add the result to the next item. Then we continue adding if we have more terms in that order, right? So this is what we are doing here. We have a double produit vectoriel. So it is we have 2 vector products. So we have 3 vectors. So here I've put, here in brackets, we have the vector v and the vector w. So this double produit vectoriel evaluates to what I have on the right here. So it's like a formula. It's like a formula. This is how you calculate the double produit vectoriel. Now, of course, we are not interested in deriving this formula or anything like that because it's not the objective, right? The objective is to start talking about things like cinématique du point matériel and all that good stuff, and applying these already established, these formulas that have already been derived. Okay, l'objectif it's not to find, it's not to sort of like derive this formula. So it's like a formula that I'm giving you here. So I'm just giving you a way of sort of like remembering the double produit vectoriel, because all you have to do here is perform the double produit vectoriel here and do it there. But then this is equal to, so the formula that is on the right hand side here, it's the dot product here. So it's a formula, so you have to respect the way it has been presented. So it is the first vector here, u. I take the dot product with the third vector here, or the second vector in brackets, which is w. And then the other vector that is not part of the dot product comes out, like the way I've represented it here. So v comes out like so. And then I'll put a minus. It's a formula. So you have u dot v and then multiply outside by w. Now, what does a dot product give us? So this is just me explaining more, trying to sort of like shed more light on what is happening here. What does a dot product give us? A dot product is going to give us a scalar. U dot v is a scalar. The dot product gives us a what? The dot product gives us a scalar. So here we have, so we'll scale this vector v by some quantity alpha. We'll also scale this vector w by some quantity beta before taking the difference at in the end. Right? So this is multiplication par un scalaire. On the this part here is multiplication par un scalaire. If we evaluate this dot product, la même chose for the other one. It's a multiplication par un scalaire and then w. C'est bon? Je passe?
Yeah.
Okay. The others?
Just to ask, here when we do, we use this format, you use when you find the produce scale,
Okay.
then we subtract both of them after we find them.
Yeah. So you say u dot v will give us a scalar, and then you multiply the scalar by every component of v, and then u dot v will give us a scalar which is beta. Then you multiply that scalar by every component that v has, and then you take the difference in the end. C'est bon?
Yes.
Ok. Right. Tassila, ça va? Je passe?
Yes.
Bien. Ok. Right. Right. So I can see that so the meeting is about to cut. So what we're going to do is I'm going to end this meeting, and then I'll send you another link so that we continue with today's session, so that we continue the next session. C'est bon? So we'll end this meeting and then we join the next one.